So we were trying to explain this concept of physics-informed neural network. And we started from the very basics and the idea of how do you inform neural networks about physics, about the equation that we want. We talked a little bit about the difference between the enforcing and informing. In the last episode, we actually talked about this from a bit of a more mathematical point of view. Try to understand when we are using a PINN to solve partial differential equations, are we actually getting these absolute singular condition that we expect a well-posed PDEs with boundary condition to have, or are we getting something more akin to the local minimum that neural networks normally find? So we started talking about this, and then we started talking also about discretization of the domains, right? So when you are solving PDEs around the complex domains, we impartially know how discretizing this domain affect other kind of algorithms, so let's say FEM and similar, and we started discussing and extrapolating about how does this play a role in PINNs. So we did all of this one starting from a very simple example. So this harmonic oscillator that is a really good introduction from PINNs. So go back to that episode if you're interested in starting very simple. But then we realized that those concepts that we were digging into, so basically, are you enforcing or are you informing? And the other one is, what about your domain discretization? Could benefit from a bit more detailed example. And looking for this one, I actually found out your article, because you're a great voice in PINNs. And in particular, I'm referring to the article that is entitled Extreme Theory of Functional Connection, a fast physics-informed neural network method for solving ordinary and partial differential equation. This is as author of Enrico Schiassi, Roberto Fufaro, and many others that actually joined this really great paper that, first of all, thank you for writing. It was a pleasure to read it. But even more, thank you for putting Navier-Stokes equation as one of the example that you're trying to solve with PINNs and not PINNs. So today I would like to ask you, can you tell us a little bit more about this paper that is not just talking about classical PINNs, but about this, say, different approach to PINNs? So can you also explain to me what I didn't understand of the paper, but also to the audience what is this extreme theory of functional connection in the context of PINNs? And then let's pick this Navier-Stokes example and grind it a little bit more.
Definitely. So thank you, Gabriele. Thank you for having me again. You know, I'm enjoying this say series of episodes that we've been doing, and again, thank you for for bringing up this paper. And again, I also want give the kudos to Roberto, my PhD advisor, Carl, Mario, and all the others that collaborated in doing this paper, because we all brought a great contribution to it. So really thanks to all the other authors. And so this paper, so the story, again, we could approach this in many different ways. So now I go with the one that I have in mind now, and then we go from there. The reality is as I mentioned, during the first episode, when we figured it out about PINNs, that what they were and how they were used, etc. We were already working on this paper. So we start working on this because the three of the authors, so Carl, Hunter, and Daniele Mortari, they were working on the theory of functional connection. Actually, they invented it. Daniele, Professor Mortari invented it, and then his amazing students, Carl and Hunter, brought it, really to the sky and to the stars and beyond. And on our end, in our group in Arizona, I was only me, and with Roberto, we were trying, to figure it out, methods to kind of simplify the way to solve differential equations, try to implement machine learning in it, etc. And at that time, Roberto...
So putting a pin on the pin, can you explain quickly what the theory of functional connection is? Very few words, and then we go back into how you implement it. Yeah.
It's actually a general mathematical framework that you can apply to any mathematical problems to when you need to approximate a function or any sort of problem like that. What the method does, essentially approximate whatever mathematical object in two parts, two functionals. A function that is completely free, you can pick whatever you want there, and like a functional that no matter what, that analytically satisfy any given linear constraint or integral constraint or whatever kind of constraints you have. And therefore, and again, that's just a complete general framework you can apply to any mathematical problem. But of course, given also the expertise that those folks had, like the straight implementation was, let's apply to differential equations. And apply to differential, and again, from ODEs to PDEs, whatever, because it doesn't matter, it's like a multi-dimensional framework, so you can really be applied to any dimension. And when it comes to differential equations, there is that part, the free function. They say, okay, this function, with differential equation like Lagrange or in general orthogonal polynomials like mainly Lagrange and Chebyshev, they work very well. And so they start with that. And then like the intuition that Roberto and I had was like...
And this is the approach that you normally use to, in the end, then integrate the equation itself, right? So express this as two terms, and then this becomes easier to integrate.
Exactly. Exactly. And the things, and again, the way you were doing that is like through essentially, you were building like what they call like a loss function or residual, which essentially like is the mean square error over the differential equation is its implicit form. And going from there, if the equation was linear, then you end up reworking your system. It becomes like AX equal B, so invert a matrix and voila. It's a simple pass least square, you get it. While the problem is non-linear, then it reduces down to like an iteratively square method to them.
Exactly. And what we are here is something very close to the typical methods that we always pit against the PINNs in this series, right? Okay, I have my set of differential equations and I just try to integrate them as, let's say, explicitly as possible, making some numerical approximations, right? But just going through that. And then something sparked on you and said, okay, these can actually get in touch into the structure of a neural network, right?
Because the idea was like the intuition like Roberto and I had was like, okay, but if this framework, you have like a free function, and that function can be anything. I mean, why don't we plug like there instead of an orthogonal polynomial like expansion, we just apply like a neural network. And that one again can be any kind of neural network, like then indeed like the Carl, for instance, tried like to plug there just a classic deep neural networks, and then with Roberto we try, why don't we try like extreme theory functional connection, which is like a controversial like neural network framework, which essentially you have like a single layer, and you randomly pick input and input weight and bias, and then the only things you need to define are the output weight. And Roberto, I knew this method because he figured it out in a conference where actually one of the professors that is considered, that there's some like people say it's him, it's not, but let's say I consider him like also the inventor of this method. They met and then like, so Roberto was using it, so we say, okay, let's do this. Essentially we try to do like a 1+1, these two frameworks to try to overcome.
And that's, I think, it's very interesting as an approach because it's kind of extreme, as you said, because when you think about neural networks, you already think about deeper structures than that. On the other side, a neural network are often seen as, you mentioned once of the previous episodes, as universal approximators in the sense of, as I was putting it in a bit of a barbarian way, the structure is so complex that then can kind of fit any function, right? But when you limit yourself to one layer, of course, you lose a lot of this, in theory, flexibility of going through very complex function. But on the other side, you get a behavior that is almost linear at when, let's say, as long as your activation function allows it for it, right? So you lose this kind of having this nested loop of activation function of linear terms, activation function of that one, and then it becomes just, okay, if you fix your activation function, the way you are changing the inside becomes almost a linear relationship. Then depending on your activation function, you can see this non-linearity on the output becoming bigger or less. But let's say it's very interpretable for being a neural network, right? So when you choose only one layer, one of the strengths is that the output becomes very, very interpretable.
Yeah. No, exactly. But the thing is there, like as you say, through like neural networks are proof, to be universal approximation. I mean, there are theorems that proves it, and then they say essentially the theorems I say, or even for let's say the less people mathematically involved, which I'm one of them. Like I leverage mathematics. I am not like a mathematician, but essentially the theorems say neural networks can approximate any like continuous function. And that the same apply for extreme learning machine. I mean, there is like a paper, and again, I can give you, we can put then the reference to the paper. Is a very interesting one, the one where the method was introduced. And then there they prove that also extreme learning machine are like universal approximators. And it's interesting, actually, it's interesting that the other episode didn't get recorded because like I'm constantly actually been in touch, and I'm constantly in touch with Professor Wang Bing, which is the inventor of extreme learning machine. And recently talking to him, he's working a lot of like how AI is like affect the brain and neuroscience and that kind of things. He's doing like an amazing job there. And it was talking to me and one of my collaborators, Francesco Calabro. I was telling us, when I invented the Helm, I was try to find the connection between brain and artificial intelligence. And indeed, if you want, then and he was say the way Helm learn is more like similar to like a human learn, because it's very fast, and you don't need a lot of. Imagine like when I tell you, okay, these are like headphones and this is a hand. Like a human, you can just explain the difference. You show them a few examples, and there we go. And essentially, like the extreme learning machine kind of work like that. Is very, very fast. So actually, then of course, people find out that it can be used.
Exactly, because even I would say from a very rule of the thumb or boxed or very far away, this way also allows you to, let's say, for a given set of input, generally have much less neurons than a deeper neural network, right? So of course you can make this layer as big as you want, but let's say it doesn't scale like the others. So I would also expect it to, even if you wouldn't give this some equation to train on, so if the loss function is barely a database, to be something that would require much less data to actually properly tune the parameters.
Yeah. It really depends, and again, like it's really let's say application dependent, I would say, because again, and you know me, like I'm a try and fail or a succeed and fail guy. So I try things and then I try to get bored, and then like I figure it out. That's what we did also with extreme theory of functional connection. It's not that at the beginning we start thinking, we need to be like a framework that mathematically is solid and blah, blah. We try, and we start, putting out application on application, then we start also working on the theory behind to try to figure it out. I think also in one of the previous episodes we can like start talking about the generalization error bound and that kind of things, but I don't want to digress too much now, but yeah, that's the idea. So yeah, and coming back, to the extreme theory of functional connection XTFC, as we call it, story, was okay. So we were working, okay, let's try to, essentially, when Roberto and I thought to put extreme learning machine there in the TFC framework, was like because we wanted to overcome the main limitation of the TFC framework applied to differential equations when it comes to PDEs, because you know that when you have Chebyshev polynomials or orthogonal polynomials, when you start going up with dimension of the differential equations, you are affected by the cost of dimensionality. And this with neural networks doesn't happen. And same, no matter whether it's deep or extreme learning machine. And that was the idea. And then like when we start working on it, so we were say, okay, now let's bring TFC, let's make like a customized version or like a TFC version with extreme learning machine for like a PDEs, actually high dimensional PDEs. Working on it, we figured it out, of course you start simple, and we figured it out it was working very well also on ODEs. So XTFC was really, let's say, a subset. So again, from the TFC perspective, you can see TFC as this big, huge mathematical framework that can be used for any mathematical problem. Then within the mathematical problems, you have the differential equations, and then TFC applied to differential equation. And within there, we have this, XTFC framework, which is like leveraged neural networks. And so that was our, the way we were, framing it and go with it. And then, boom, arrives the PINN, the paper from the Brown group, Raisi, Perdikaris, and Karniadakis, where they were introducing the PIN, and again, they're great. They leverage on an existing field. Like people were try to at least pinch on how to use neural networks to approach differential equation. Even at least that I know, the oldest paper go back to the beginning of the 90s. But then, of course, there you need the reason why they exploded, let's say now, is because you can leverage the automatic differentiation technique to then, like also take into account, the partial derivatives of the differential equations operators. And that's why, they really boom. And then the Brown group came up with this amazing, naming things on a physics informed neural network, which was like an amazing idea, amazing way to sell it. And then with Roberto, we start thinking, maybe we can also, we can consider this, being a framework within the physics informed neural networks. And then it was cool, we were excited about it, and we went with that, which, at the end, it depends on the way you look at it, it is true anyway. So, and then we go with that, and we start, building applications. And again, try and fail.
And let's say to sum it up, let's say on the main differences from the architectural point of view, I think you said it really, really clearly. It's let's say imaging instead of a deep neural network before you start the differentiation part and everything. You just have one layer that is supported by basically this theory that you realize, okay, it clicks. It's actually I can use it in the same way. On the, let's say, how to use it, or the normal, let's say you have somebody that knows how to use pins, for example, and what should he expect different from using this other method? Is it something just normally faster and normally, let's say, with more interpretable, or are there other differences? Do those differences exist? Are you actually faster or more interpretable?
Yeah. No, that's a great point, and I'm glad that you brought it up. I was going there, but thank you for stopping me and asking the question, because then we made the point clear. And there they say, then, when we decided to go, like framing thing as a pin, we say, okay, we need to then figure it out. How can either improve or, assess or make better the pin frameworks. And in general, you see, the way I see PINN has two main groups of limitations. So one is the fact that they brought by using deep neural networks. And the second one is having the boundary and or initial condition to be included in the loss function. So with extreme theory of functional connection, you can get rid of these two main limitations. Why? On the deep learning part, the main issue of deep learning is, as you say before, when you introduce a deep neural network, you introduce complexity. The fact that you have function within function within function at the end of the day, this brings complexity and non-linearity, even when the original differential equation you need to solve is linear by nature, okay? And therefore, with XTFC, this is removed, because if the differential equation is linear, you solve it as a linear problem. And therefore, that you maintain all the nice things when you have something linear, which is convexity, right? And therefore, if the problem is linear, with XTFC, you're depending on but you are kind of guaranteed that the problem gets solved. Now, on the boundary condition side, with the boost comes from the TFC part, they are analytically satisfied. So you don't have to take them into consideration within the loss function. So you also reduce, you make it faster, because you have some terms less, and therefore less data to take into consideration. But also you avoid the fact, especially when you use the PINN as, let's say, brutal, let's pass me this term, as brutal differential equation solvers, because when you don't have data, experimental, real data, they are differential equation solvers.
Yeah, indeed. And this to me sounds like a really big deal, right? Because that was one of the main points that make pins interesting on one side. If you use them as, I want a neural network and I want to inform this neural network of some physics, but at the same time they were always unable in general to perfectly enforce the physics, right? Because of this kind of tension between the element of the loss function that is I want to satisfy the equation and the element of the loss function that says I want to satisfy boundary condition. If you tell me that you can then analytically satisfy both of them, then it becomes something that could actually enforce physics. That for some kind of problems, imagine problems of combustion where the mass of the combustant is something that you have to get exactly right. It sounds like potentially very powerful.
Exactly, and indeed, actually now, like while speaking, so in this one was not, I didn't even think about it. I just came to my mind by speaking to you now, and like leveraging on the fact that, let's say TFC, and again here I'm talking TFC. I'm leaving the AI, machine learning, whatever out of the equation. Just think about TFC. With TFC, you analytically satisfy any given constraint. So now imagine the combustion thing. You have a set of data that you trust. Then with TFC, we could consider them as all constraints because they can, you can do that with TFC. I mean, it's not then gonna be easy that to code, because then we can go many multi-dimensional, a lot of constraints, blah, blah. It's not that easy.
I'm happy to leave the coding to you. Yeah.
But, well, actually, we're throwing the ideas out of there. Maybe some of the people that listen to us, they may try. But in theory, you get all the data, you trust the data. Let's say you need to trust the data to do what I'm about to say. And then with TFC, you can make sure those data are analytically satisfied. And therefore, as you say, then we are left only with the equation part that then you enforce it through the PINN.
Yeah, exactly. And then to me, coming back in my days when I was still a young student of CFD and focusing on numerical method to solve PDEs, the always struggle is you need a framework in which you can prove that as long as your, let's say, discretization or numerical assumption are fine enough, you are actually smoothly converging to that unique solution of your PDEs plus boundary condition, right? So that's a really big deal because just finding one solution, there is not this solution, otherwise it's completely useless because you say, I found a solution where my thing works and I found out another solution when you said, okay, people are going to die in this room, right? You cannot work like this. And the idea, if I understood correctly, is that what you're trying to bring with these other pins is something in which you can prove much better the smoother convergence once you change, for example, input size or similar, because you can exactly converge to that solution itself at the minimum of the domain discretization. Of course, that's
exactly. And indeed, and again, now not to go out of topic, but we figured out, also some bounds on how well this framework generalized error. Indeed, in that bounds, one of the term takes into account how well the training, but then essentially the loss function, the loss of the training is. But the other term takes into account exactly the discretization of the domain or the way you handle the domain, because there, of course, now we work it out very well for the ordinary differential equations, but in that there is exactly the terms that show you that the error gets low, the generalization error bound gets lower if, of course, as you say, the domain gets smaller, which makes sense, of course. And indeed, exactly, here you can see, these two things brought together, but the reality is that they're not, as has been saying since the beginning, I mean, it's not really and I think we ended up, we all started this because, okay, you defending the classical method like FEM, me defending the PINN method, but reality is these two methods are very similar under many different aspects, and they really can work very well together. So I think we're gonna end up with a tie at the end of the day.
Indeed, and this is just gonna be a dear to engineers problem of resource optimization, how to get a spin-off. But actually, let's move on that article of yours. Actually, on the example you've done with Navier-Stokes equation, because I think on that side it was pretty clear right now that this particular type of pins have some potentially a really huge upside, and I always feel like selling something too much if I don't always think about downside or areas in which, let's say, traditional methods, traditional pins, or these pins could face each other, and when one is better than the other. And you took a quite interesting example from fluid dynamics and something that normally FEM or finite volumes could fix, but you are actually trying it out with various level of pins. And I think that's is great in the paper because it really shows the kind of trade-off. Can you tell us a little bit more about that? Yeah.
So yeah, I mean, I'm knowing you. I know, of course, you're referring to the Navier-Stokes equation example.
Absolutely.
And there is also like another one, which is the Burger equation. And there essentially we wanted to stress the method on, how well you can capture, let's say, like non-linear, or where like very, especially on the Burger equation actually, where you have like shocks, right? So your solution at some point becomes like heavily discontinuous or become discontinuous. And of course, I mean, this is where like many methods struggles, because we know that they are all methods that, let's say, they are like, again, I'm saying it brutally, but as an engineer, I want to make things, clear and practical. So the methods where they are derivative based, because here we deal with derivatives. Of course, when there is a discontinuity, the derivatives, gets crazy. So in that we try, and then we try both, the XTFC and the deep TFC, which is like the companion of XTFC, where the free function part is a deep network. And of course there, both they were good to solve it, when the discontinuity was not that bad. And actually that XTFC performs better. And then when the problem started to become very, very highly discontinuous, XTFC started to go banana, while like TFC kind of worked a little bit better. So when we saw this behavior, of course, the very first thing that comes to my mind, to your mind, to everyone's mind, was like, okay, wait, but it makes sense, because, as also you say, like when you have a deep network, the extreme part is shallow. So say when the behaviors becomes very nonlinear or very, let's say, complex, maybe something that as a structure is more complex may kind of try to mimic it better. So for that is a fair point and might be there. The reality is that with the computational resources we had, we never were able to, push the neurons higher too much in the XTFC. So really we don't know if we had that possibility, if XTFC would have solved it.
Yeah, exactly, because this makes me think about one classical example that I think was, you still have two parties in the classical fluid dynamics, like FEM and volume of fluids. Volume of fluids being a much simpler, let's say, method that doesn't try to use, let's say, advanced or particularly complicated shape functions to represent your actual equations. And so basically you can roughly think about in FEM theory, people from the FEM side see volume of fluid as a dummy FEM, let's say, representation, one with simple function itself. Volume of fluid people will not really agree on that one too much, but let's keep this unpolarized. It's true that volume of fluid does not have shape functions that are particularly complex, right? And the interesting thing for me is that despite fluid dynamics problems have been addressed with the finite element method, so the one with the more complex shape function that allow, let's say, to represent functions that are more complicated for many years. And theoretically, on the mathematical point of view, you could see the case of allowing shape function to be more complex should allow you also to get let's say, more complex function resolved or represented in this subdimensional space. Actually, finite volume methods are still extremely widely used, and these kind of link into the fact that fluid dynamics by itself is physics that can represent a lot of nonlinearities, right? And sometimes to capture these nonlinearities using a simpler method, but with a higher discretization, is actually more effective and robust than using a more complex method that allows to have fewer discretization. For sure, and I think that's what you were saying, nobody will try to solve the same problem with the same number of elements with the finite elements and finite volume. And that's maybe what you actually were doing here, right? So you were trying to pitting together a deep network and an extreme network, but you didn't allow the extreme network to have a finer discretization of the problem, because again, there I would say then it becomes a lot of a cost kind of cost reward situation in which you have to say, okay, let's say that I have to use a finite discretization for my extreme, right? But extreme is so much cheaper that can allow me to do this. So it should be something quite interesting to try.
And exactly, and here it's not that you open a door that is already open, you're like making it explode, because I'm exactly like, and specific thing also for the two of us that we went from research in university and then to industry and the corporate world, and then you see people want stuff that works and are efficient. And this is the case, I think, like you don't need to go too complex, too fancy. And even is a little bit, in the AI world, if you want to go philosophical between, the model-centric, data-centric kind of things, or if you want, the artificial narrow intelligence versus the artificial general intelligence. Of course, I mean, it would be cool, if you have something that a sort of oracle that knows everything, knows how to do everything, but that's not the case. That's very difficult, and maybe we get there.
That's something that we start seeing more and more also in this more complex level, highly complex side of machine learning, that is on the large language models. More and more companies are working on different sides of network. There is the Haiku, Sonnet, and Opus of Anthropic that clearly try to do that one, like to try to acknowledge the fact that just having bigger networks all the time is not something sustainable and not something that you want to do that. Of course, we're talking about different complexity, but
but at the end, and again, like and this again is my point of view, so I'm not saying it's right or wrong, just my point of view. I like simple things that are efficient, and I think for instance in this case, like the XTFC. It's simple, it's efficient because it's fast, it has a lot of good properties, plus, and then and something that again I started to do on the ODEs side, because again there you have a lot of ODEs that are like present very either stiff or have like high discontinuity, and so there I started to do so like with my friend former co-worker Mario De Florio, we started working on the ODE side on that, try to apply domain discretization exactly to kind of like manage this kind of complex behavior. Actually, we succeed very well. There are a couple of papers that we are out. One is the one where I introduced this methodology that is a paper I led on stiff chemical, point kinetics equation for nuclear reactors. And then there is another one, very amazing one that then Mario led, was about stiff chemical kinetics. And again, the framework that we work out for the point kinetics one, we just applied straight on the stiff chemical kinetics, and we were able to do to solve problems where normal methods there fail. So those are two interesting papers. Maybe we can discuss more about that. Maybe also have Mario to discuss with that about those.
That sounds like a really great plan, and actually makes me think about one question I asked in the very first episode, right? That was for people that would just like to try things out, understand a little bit the world of pins, right? Where can you actually start from? And now you're making me think that, wait a second, so if I have the method that you are actually working on, that is relatively architecturally simpler, right? And has all these very good properties that some people will actually like to start from, but of course is limited in the complexity of physics to solve. I think you're actually right now answering quite well that question. So I think extreme theory that you're working on could be a great way into the vast and larger world of pins, but it allows you to have something that is likely very stable, resolve analytically or includes and satisfies analytically the boundary conditions, and at the same time probably a little bit more interpretable than a very deep network. Yeah.
And also another great property is that now thanks to the way it is expressed through the extreme theory of functional connection. So you also could all the part that when you deal with deep neural networks need to be taken care of from the automatic differentiation. So essentially computing the partial derivatives of the question, and in general the derivatives of the differential equations. In theory, with XTFC, because of the extreme learning machine, you can also handle that part analytically. So that one is again a way to remove numerical parts within it, so keep it again simpler, lighter, whatever. Then is a pain to doing it. So usually what we were doing we were like, especially with working with PDs, we were still using automatic differentiation, but just for like prototype purposes. Because then when we wanted really to train and see how was the performance, we were then doing that analytically. But for prototype purposes, we're doing it because it's very easy that you do a mistake when you compute like manually a derivatives. But again, that's another amazing properties that you have. So to keep it more simpler.
That sounds really good. So anybody that would be interested in entering this work can directly message you in one of the apps, and you will definitely help them building this stuff up. That's really cool. I think right now this 3 episodes gave, at least to me, quite broader introduction of PINNs and also the specific field of PINNs that you're a particular specialist in. And I think that the paper that you wrote is a really, really good one. So I recommend people really to read it and cite it, of course. That's always makes everyone happy. And I think that another things will be interesting in the next episodes, or after we are moving on from the Christmas break, would be actually to start seeing applications even outside papers, right, of people trying to use it as technology to really change the way they approach differential equations. But for the moment, I think this is another about 30 to 40 minutes episode. It was, as always, really cool talking to you about the things you're so passionate about. So really, thank you a lot, Enrico. You are expanding my mind on this field with every single episode.
Awesome. Thank you, Gabriele. No, I enjoyed as always, and looking forward for more episodes. And again, I totally agree with you. Would be cool to have see some real world applications. I know some that are happening, so it would be cool to bring somebody in.